Welcome to CS225. This lecture will be on red-black trees, again, just like the previous one. In this lecture, we'll be discussing the removal of nodes from red-black trees. And again, we will be trying to tie this into the idea of removing from a 2-3-4 tree, and so we will be addressing the same sort of cases that we dealt with when we talked about 2-3 trees and B trees, namely removing from a node and not causing underflow, or causing underflow but correcting it with a steal operation, or causing underflow but correcting it with a combine operation. So let's put our original, the kind of tree we were drawing back again. We had here, this was from the last lecture, we had 20, 50, and 80. And here we had 5 and 10. And here we had 2, 7, and 8. And 12, 15, and 16. And then there was a subtree A here, and B, and C. And so we're not going to draw those in just like we didn't draw those in last time. And so we said then this would be represented with a tree. We convert the 20, 50, 80 node to a collection of nodes in the red-black tree like that. We had converted the 5, 10 node to a collection like that. And then we had 2 as a child. We had 8 as a, let me even out the levels here. We had 2 as a child. We had 8 with 7 as a left child. That was our 3 node. And then we had the 12, 15, it's kind of ugly, 12, 15, 16 node here. And then we'd have here, this would be our subtree A, and I did this last time too, I didn't space these out well enough. This would have been 50, and we would have had 80 here. And so there's subtree A, and this would have been subtree B and C, whatever those subtrees would be. So we're dealing with this again. Now, the way we're going to begin the removal algorithm is by doing a binary search tree remove. So we will once again start with that binary search tree idea. We'll come back to this picture. So to begin the remove, the first thing we do is a binary search tree remove, which, remember, is never going to delete nodes with 2 children. The binary search tree node always made sure that when we did a removal, the removal always began by either finding the leaf or the 1-child node where our value was located, or finding a 2-child node and replacing items with the in-order successor. So what we will be deleting here, we're guaranteed we are deleting a 0-child or a 1-child node. Now, once we've done that, if the deleted node was red, then we can stop. Before we even look at the tree, remember the principles that we had to keep intact for the red-black tree. We said that there could not be 2 consecutive red nodes. Every red node had 2 black children and didn't have any red children. Well, deleting a red node can't create 2 consecutive reds. That can't happen. There'd be no way you would have done something like this. This would have been a tree horribly in violation to start with. So you can't say, hey, I've gotten rid of this red node and now there's 2 reds consecutive. There would have been 2 reds consecutive anyway, if that had been the case, and that wouldn't be allowed. So there's no way deleting a red node could create 2 consecutive reds. And if we delete a red node, the other principle that we had to keep intact was that we had the heights, the number of black nodes measuring from a root to any leaf had to be the same. Well, deleting a red node can't affect that. So there's no problem there either. And so therefore, if the deleted node is red, we can simply stop. And so going back to the picture, we can see examples like that. For example, if I'm going to get rid of 12 or 16, if I decide to get rid of 12, I say, well, whoops, I want to just scratch it out. If I decide to get rid of 12 here, that reduces the 4 node, 12, 15, 16, to a 3 node, 15, 16. And what we would be doing there is getting rid of this node, getting rid of the red leaf. Well, getting rid of a red leaf is not a problem. That's just gone and that's it. So we would stop. Similarly, if I then, either before getting rid of 12 or after getting rid of 12, decided I'm going to get rid of 16 as well, if here I convert the 3 node to a 2 node containing just 15, well, again, I'm getting rid of that. There's no problem there. So I could have just deleted that. So deleting our red leaves here isn't a problem. We're not going to delete a red node with 2 black children because we don't, in a binary search tree, delete 2 child nodes. So those won't be concerns there. But we've got a situation here as well where, let me kind of draw those in. If I had deleted 15 from this node, oops. If this 4 node, instead of getting rid of 12 or 16 and deleting red leaves, if I had decided to get rid of 15, leaving me with a 3 node of just 12 and 16, well, the way this would have worked is, in this binary search tree, we would have said, I can't actually get rid of the node containing 15. That's a true child node. I'm going to replace it with its inward successor, which is 16. And actually, it's being filled into a black node. So 16 used to be in a red node, but now it will be black because it's inside a red node. And then we would have gotten rid of where the inward successor came from. So you would have ended up with this tree, where that leaf is gone. And what you have here is 16. And now you have the 3 node 12, 16 represented by 16 at the root and 12 as a left-right child. And that would be okay. So no matter what you're doing to a 4 node, if you remove a value from the 4 node, you'll be fine. Because either you're removing one of the 2 red leaves, if you're removing a value, if your leaf is a 4 node, if you remove a value from it that's one of the outer ones, either the leftmost of the 3 values or the rightmost, that would just be deleting a red leaf. And if you remove the middle value of the 4 node, we'll end up doing what we did here, where you don't actually delete the node containing that middle value, you do the inward successor swap, and you're still, as a result, removing a red leaf. And then likewise here, in this case, if I decide to get rid of 7 for the 3 node 8, 7, I just get rid of the red leaf there. So if I had gotten rid of 7 here, that just means, okay, now I shrink to a 2 node containing 8, and that's what I've done here. 10's left child is just a 2 node containing 8. There's no extra children off of 8. That would mean that those values would also be in that node. So those would be some of our examples of easy underflow cases to deal with. We're removing red leaves so nothing happens. Otherwise, if we're not deleting a red node, then we are deleting, we kind of say else. Else we're deleting a black node. And what we will do here is then say what the parent of that node now points to, call it X. So what we're saying is, in this case, if this had been the node, well, it would have been a black node. So let me sort of redraw that. We're saying in this picture here, if I had had some sort of situation like this, where I'm deleting a black node, if it was a one-child node, the parent would point down to that one child. We call that X, the child of what we deleted. If, on the other hand, we are getting rid of a leaf, if we get rid of that, well, then the parent will now point to null. We call that null X. So that's all we mean with this X idea. We're saying, okay, the parent used to point to this node, but now we've gotten rid of that node. So what does the parent point to now? Well, the parent either points to the one child of that node if it had a child, or the parent points to null if the node we deleted was a leaf. And so either that one child or the null will be considered X. And then taking X at that point, we will then proceed to run our various algorithms fitting patterns to that. That'll be where we start with X. So it'll be like the remove algorithm where X was some node, and we asked about, okay, now look at the pattern formed by the colors and the existence of the sibling of X and the parent of X and the sibling of that parent and the grandparent and all those sorts of things. That'll be what we're focusing on here. And what we'll say is then, while x is not the root and x is black. We'll have our cases in here, and that's what we'll talk about next. When we finally exit this while loop, we will exit it because x was the root, or because x was red, or perhaps both. In any case, when we're done, we're going to make sure to color x black. So if we exit the while loop because x has turned red, no problem. We say, okay, well that caused the while loop to exit. We'll simply color x black. And so that shows us another really easy case. What happens if we say, okay, the deleted node wasn't red, it was black. We call the sort of child of that node x. And then we say, well, what if the while loop exits right away? What if, okay, well, we have a big tree, so x won't be the root right away in our example. But what if x is red right away? In that case, we would exit the while loop immediately and color x black, and we'd be done. This is the entire algorithm right here, aside from the cases we have to fill in. But there's nothing else here. This is it. That's the remove. So, for example, let's put 7 back and say what happens if instead of deleting 7, we deleted 8. We had this tree with 7 here. I'm putting the original tree back. This was 16. And then here we had 15. Wow. So, what happens if we delete 8? There shouldn't be any appreciable difference in this node between deleting 7. When I deleted 7, I was left with 8 in that node. If I delete 8, I'm left with 7 in that node. In the tree, however, there is a difference between the values 7 and 8 because 8's the root of this little mini thing and this little mini tree, and 7's the red left child. So if I get rid of 8, I say, okay, well this is a one-child node, so what I'm going to be doing here is saying, I'll point this in blue, this parent should be pointed down to the one child of the node we're getting rid of. So that when we get rid of it, didn't want to do that, the parent should be pointed down to the one child of the node we're getting rid of. And that node right now is colored red, so this is what we've got here. 7 is now the direct child of 10 rather than the grandchild of 10. That was the consequence of deleting 8. When we delete 8, 10 now points to what 8 pointed to, which was 7. And then we say, well, what that child was, what the parent now points to, we call that x. That's what we said here. What parent of that node now points to, call it x. So what 10 now points to, call it x. And we say, well, the node is red, color it black. And that's it. We're done. Let me redraw the node as a black node now. But that's all that has to be done here. We simply say, okay, the node's red, colored black, and we're done. That's what this said. X was red, so we left the while loop immediately. Should be parentheses there. X was not black. That case was false. So we left the while loop immediately. We came down to here. We colored X black, and we're done. And that's what's happened here. We basically, by getting rid of the node 8, we lost a black node along this path. Now we need to somehow, somewhere, add in another black node in a way that adjusts the tree. Well, if we've got a red node at our disposal, just color it black and we're all set. And so that's what's happened here. And you can see then that now we have 5 and 10, just as we've always discussed. These are part of one node. Your red child is always part of the node that's its parent. So 5 and 10 are part of one node. 15, 12, and 16 are one of the children of that node. 7 alone is one of the children of that node, and 2 alone is one of the children of that node. And that's what we see up here in the 2-3 tree. 12, 15, 16 is a leaf, 7 is a leaf, 2 is a leaf, and all 3 of those leaves are children of the 5, 10 node. So that's the other way that no underflow in a leaf might have been handled. When we say here basically, either your node was red, if what you're doing represents no underflow in a leaf in your 2-3 tree, 2-3-4 tree, then either the deleted node was red, or it would have been black, but when you deleted it, what it pointed to would have been red, and you'd exit your while loop immediately. The while loop we don't go through the while loop if there was a no underflow situation. Only when you're going to have to steal or combine. So you either don't even hit the while loop to begin with, or you do hit it because you deleted the black node, but your condition for the while loop would be false, and you don't actually go through it. And so that's the equivalent. Those would be the two ways in which we handle our no underflow cases. So let me put the tree back how it was. We had here, that wasn't there, that's gone, that's gone, that's gone. And we have here 8 and 7. So here's our original tree again. And now we have to deal with the cases. What happens when you enter the while loop, when either x is not the root and x is black? So for example, what if we delete 2 from this tree? 2 is less than 50, less than 20, less than 5. We get rid of 2 and the node that held it, and 5 now points to null. And that's sort of the equivalent in the 2-3 tree of erasing 2 from a node, and that underflows this node. Because it was a 2 node, now we've removed a value, so it drops. It's now going to have sort of 1 null child and 0 values, and we need to do something about that. So that's our situation. Now, there's sort of 3 cases to deal with. We have a steal and we have a combine. So in the cases where we combine, or steal rather, and you'll notice because your immediate sibling doesn't overflow, you actually can steal here. There's going to be some work we have to do for a steal, but we'll stop after ultimately the last situation. And there'll be some work we have to do for combine. So if we end up with a combine case, we'll do that as well. However, before we can either deal with the steal or the combine, there's some other case we have to deal with first. And so when we talk about cases here, we're going to have 4 cases. We'll sort of have a 1, which is not related to, this will be sort of a setup if needed. And I'm going to discuss that first, because we will need it here. And then 2A and 2B, those cases will be the steal cases. And then I'll show case 3, which will be the combine. So it's really, 4 separate, the 2A and 2B are separate cases, but they're part of the steal, so I'm going to call them sort of 2A and 2B rather than 2 separate cases. So 1 will be just a generic setup if it's needed, and then that'll launch us into either doing 2A or 2B or 3. So we have our steal and combine cases, are just the setup that we have to talk about. So what kind of setup do I mean? And what I mean is, there are situations that we need to correct immediately before we launch into 2A and 2B. Stealing and combining always dealt with a sibling. If this node underflows, we would steal from that sibling, or maybe we combine with that sibling. And those were the situations we had to worry about. However, we can't do that in this tree. And the reason is, this sort of represents our underflowing node. The sibling in the red-black tree isn't really the sibling of this node. Because of the way we structure things, we say, well, 10 is really part of the node containing 5. And we see that right here, but it's clear here as well. It's a red node, so it's part of the parent above it if you convert it back to a 2, 3, 4 tree. And yet 10 is the sibling of this null child. So since 10 is the sibling, what we're really saying now is the way the red-black tree is arranged, siblings in the red-black tree are this node and this value here. And trying to compare those two and deal with them in terms of steals and combines isn't going to make any sense. 10 shouldn't have anything to do with this node down here. So what we need to do is recognize our 3 node is sort of tilted the wrong way. It would have been perfectly reasonable as well, and I'm going to delete this whole section of the tree now. And you just know, okay, there's more stuff. There's more stuff here. It would have been perfectly reasonable to have restructured this tree, or to have it structured to begin with, where if I had 20, 20 could have been pointing down to 10. And 10 would have been pointing down to 5, and then had your pieces. So 5 would now be null. It used to hold 2 there. This would be 8, followed by 7. And then this would have been 15 with 12 and 16, not 26, with 12 and 16 as children. In that situation now, all we've done is we've tilted this the other way. If we had had the tree set up like this, we wouldn't have had this problem. Here's your x. This is our x value here. This would have still been x, but now the sibling of x in the red-black tree actually is part of the actual real sibling of this underflowing node in the 2, 3, 4 tree. And that's what we want. When we compare the siblings, we want to actually be comparing real siblings, not like we're doing here where we compare x to 10. We're comparing the underflowing node to some other value way up in its parent. We don't want to do that. And we wouldn't have had to if the 3 node was tilted like this, with the second of the 2 values as the root and the first of them as the left child. But instead we have the first of the 2 values as the root and the second of them as the right red child. So case 1 will involve taking this situation and converting it to that one. And in order to do that, take a close look at what we've done here. All we've done is a rotation. We moved 10 up to become the root of this, consider the subtree rooted at 5. 10 has moved up to become the root, 5 has moved downward to become the left child, and the subtree 8, 7 moved across. What we've done here is a single rotation on 5 towards x. And that's what we're going to deal with here. That will be our solution to this case. We say, now we're inside the while loop. So we say, case 1. Sibling of x is red. Because that's our case here. If the sibling of x is red, that means it's really part of the node. Didn't want to draw a black mark there. Of course, didn't want to erase the blue mark either. If the sibling of x is red, as 10 is, that means this red node is really, if you were to convert back to a 2, 3, 4 tree, this red value would be part of the node above it. And we see that here. We have 5 and 10 are in the same node. If your sibling is black, on the other hand, as 8 is black, in this case, well, that means, okay, even if your parent was red, these are both actual legitimate children of that red parent. And if your parent was black, these are still legitimate children of that. Just like here, 8 and 15 are both children of 10. We see that here. The 7 to 8 node and the 12, 15, 16 node are both children of 10. Likewise here, the null and the 8 are both children of 5. Well, yes, the null, the underflowing node, and the 7, 8 are both children of 5. So when your sibling is black, that means, okay, well, you already know you're black. The node here, is whether it's a null pointer or an actual node, this is black, colored black, or we wouldn't have been going on to begin with. We would have stopped. Like when we had gotten rid of 8, we pointed to 7, but 7 was red. We changed it to black, and we were done. So we know that this will be a black node. And then if our sibling is black as well, it means us and our sibling are both children of our parent. And so we know it's an actual sibling. When our sibling is red, that means our sibling is really part of the node above it, and it's the siblings' children, 8 and 15 in this case, that are the actual siblings of our x. Just here we say 7, 8, and 12, 15, 16 are the actual siblings of the underflowing node. So that's why we have this first case where we say, is the sibling of x black or red? If it's red, then in this case, what we're saying is, oops, let me change it to black. We say, color the sibling of x black, color the parent of x red, and then do a single rotation on parent of x toward x. By toward x, what I mean is, well, we could have a mirror image of the picture I've got here. In this case, we're doing a single rotation to the left, a left single rotation. X is on the left side of its parent, so we do a rotation to the left. If we had this exact picture but a mirror image, and x was on the right side of its parent, and the left sibling were 10, well then what we would have done is done a right rotation on 5, and fixed things that way. So whether you rotate left or right depends on what side of the tree X is on, because you're trying to rotate towards X. You want to move X down and then have this subtree move across, and it's the subtree that moves across that will then become the sibling for X. So that's our case 1. We can't stop when we do this. Now this will go on to one of the next cases, but this at least does, if nothing else, and it doesn't do anything else, all it does is it retilts a 3 node. You don't say, well, what if I'm part of a 4 node, because then you'd be red as well. If you were red and 10 was red and 5 was black, that would mean these 3 were all part of the same 4 node. No problem there. But if you're black and your sibling is red, that means your sibling is part of a 3 node, which is your parent. And X is then a child of that parent, and that's what you're trying to fix here. You're trying to say, I don't want to compare to a value of my parent, I want to do this case 1 operation so that my sibling is actually black, then I can proceed with other things. And so that's what goes on here. We're simply doing a rotation and recolor so that we can retilt the 3 node. That's ultimately what we're doing. We're saying instead of representing the 3 node as 5, 10, we represent it as 10 with a left child of 5, and we then reorder the subtrees as needed by moving 8, 7 over to the other node. So that's case 1. So now, case 2 and 3, we will assume. And then so here we move on. We will move here to case 2 or 3. Just so you know, we don't stop there. Now for case 2 and 3, we assume X's sibling is black. If it had been red, we would have done case 1 and fixed that. So when we hit case 2 and 3, it's a given that X's sibling is black. And we will say that case 2, in case 2, we will say at least one of the siblings' children is red. And case 3 will be both of the siblings' children are black. And those will be our cases. Of course, now we need to extrapolate a bit on what case 2 and 3 are. But those are the signal issues for them. So either your sibling is red, or it's black but has red children, or it's black and has black children. All black children instead of at least one red. So in this situation, I'm going to now take this and write it over here. We've done this rotation, so I want to need the room to do other work. So I say, okay, this was the result. Once we did the rotation, I'm drawing that in the actual main tree here. We had rotated 10 up, we had rotated 5 down. The left subtree of 5 remained the same. The right subtree of 10 remain the same, and the right subtree of 5 remain the same. So, or actually that used to be the left subtree of 10, it moved over. So I'm going to get rid of this now. It just copied over what I'm deleting now. So that was that after step 1. Our tree looks like this. Now, here's why we have the case 2 and 3 signaled the way we do. If our sibling has at least one red child, then it means our sibling is a 3 node or a 4 node. Remember, 2 nodes look like this. You have some value and then they have 2 black children. But 3 nodes will have some value and a red child, and that was what we had here, and then those are the 3 children of the node. And then 4 nodes had some value and 2 red children, and we see that, for example, with 15. So if your node has either 1 or 2 red children, then it's at least a 3 node, perhaps a 4 node, and you can steal from it. And that's what we're worried about here. We say, hey, here's my node here. I want to be able to steal from my sibling, which is 7 and 8 in this case. If the sibling would have underflowed when I stole from it, well, that would be the equivalent of saying my sibling is black, but it has 2 black children. So it only has one value, because the 2 children are actual real children. But in the case like the 7, 8, the sibling of x, which is 8, is black, but it has 1 red child, the value 7. And that's because 7 and 8 are part of the same node. So there shouldn't be anything keeping us from saying, well, then what if I were to move 7 up? Remember how we handle the steel case. Move 7 up, move 5 down, and that's what we ultimately want to do. We want to say 7 will move into the parent, 5 will move down. And so the underflowing node now gains 5. The parent loses 5 but gains 7, so there's no problem there. And then the immediate sibling, which was 7, 8, loses 7, but it's still got the value 8, so it's still okay. There's no underflow there. And so that's what we're dealing with. If my sibling of x has at least 1 red child, then it means, well, the red child is always part of the sibling. If a sibling has a red child 7, 7 is part of the sibling. 15 had 2 red children, they're both part of the same node as 15. So if our sibling has at least 1 red child, then that means that there's at least 1 extra value besides the sibling itself. Maybe you have 8 and then something else like 7. Maybe if we had been dealing with 15 as a sibling, which we're not, then we'd have 12 and 16 as extra values. But just 1 is enough, as we see here. You just need to move that 1 into the parent and move then the parent's value down. So as long as our sibling has at least 1 extra value, we're okay. And since the extra values, the fact that it's a 3 node or a 4 node rather than a 2 node, is indicated by red children, that's why we check for that. We're saying if at least one of the siblings' children is red, then that means the sibling is a 3 node or a 4 node, and those red children, whether there's 1 or 2 of them, are part of this node. On the other hand, if both of the siblings' children are black, that means the sibling is a 2 node, and the children of that are actual legitimate children. They're not part of the same node as the sibling. And that will be our combined case. So case 2 is going to mean that we will steal, and case 3 will mean we combine. Because if I have, my sibling has a red child, I'll be able to do a steal operation. On the other hand, now, given this setup, if my sibling is a, like say 5, 7, 8, if I get rid of 5, then I would have 8 being my sibling, but 8 would have 2 null children. There wouldn't be some 7 or whatever attached to it. So that's how that works, and that's why we can do things that way. So, now let's look at the steal case. Case 2. So our assumptions are, if we're hitting this case, we know then x is black, sibling is black, and now we also know sibling has at least 1 red child, perhaps 2. So, our case 2a, if the child of the sibling which is furthest from x, now I'm going to put a comma there, is black, so that's going to be this case. If the child, if the child of the sibling is, which is furthest from x, is black, that I'm going to see if that helps. Then what this implies, implies the child of the sibling which is closest to x. Having trouble writing today. Closest to x is red. That's going to be our 2a. We have to talk about how to handle this, but first let me clear up what on earth we're talking about here. If we go back to the picture, you'll notice here you have your sibling. Now you're saying, given this sibling, it has 2 children. This is the one, 7, which is closer to x, and then you also have this null child here, and that's the one that's furthest from x. So your sibling will have two children. One of them is going to be closer to x, and one of them is going to be further. And so again, that's just generalizing the direction. When x is to the left of its sibling, then the one furthest from x is the right child of the sibling. And that's what we're talking about here. X is to the left of 8, and so the child of 8 that we say is furthest from 8 is the right child of 8, or furthest from x is the right child of 8. Right child of 8 is the further child. 7 is the child of 8 that's closer to x. And that's what we're dealing with here. If this had been flipped around the other way, then you know, if we had this situation, this was our x here, and then here we had, then this would have been the, if this is our sibling, this would have been the child furthest from x, this would have been the one closest to x. So if you're actually going to code this, you have to then realize, okay, well, left, you know, depending on whether x is to the left or right of 8, then, you know, what direction do you go deal with? But that's why I'm speaking in these generalized terms here. The child of the sibling which is furthest from x is black. That's saying in this case, since x is to the left of 8, the right subtree of 8 is black. And indeed it is. So this subtree now is going to fall into case 2a, this tree here. We're saying, okay, if in this case, the right child of 8 is black, that's the furthest one from x. Well, we had said one of our assumptions that we had when we get to this case to begin with is that, well, x is black, we know. X's sibling, which is 8, is black. And we know 8 has at least one red child. That's how we know we're in this case. Well, if x has at least one red child, but the furthest child from x is black, well, then that implies there has to be a red somewhere. We're saying we assume 8 has at least one red child. If the furthest one from x is not red, then the closest one to x has to be red. And that's the meaning of this statement here. If the child of the sibling, which is 8 in our example, is furthest from x is black, well, one of the children of the sibling has to be red. That's what we assumed by starting case 2. If they were both black, we'd be in case 3. So if we're in case 2, one of the children of x's sibling is red, at least. And so if the one further from x is black, then that implies the one closest to x has to be red, because one of them has to be red, and it's not the furthest, so it's got to be the closest. And that's what we're saying here. One of the two children of 8 is red, because that's why we're in case 2 to begin with. It's not the furthest one away, so therefore we know then this has to be red. And we're going to handle that again by doing conversion. Just as case 1 converted things so that we could then run case 2a or 2b or 3, now the whole purpose of 2a is simply going to be to convert the tree so that case 2 can work. Because ultimately what we want, as we said, is to move a value from this leaf into the parent and from the parent down to that leaf. And if you were to do a rotation, you'd move x up into a parent and the parent down. So imagine doing a single left rotation on 5 and perhaps doing some recolorings while you're at it. Well, what you might have here now is, if you were to do that rotation, you might end up with, here's 10. Let me erase this stuff. You might say, okay, well, here's 10 pointing down to, and you might say, okay, 8 is my node there. I point down to 5, which holds a null. 7 moves over to become the left child of 5, and then 8's right child is still null. So if we do this rotation on 5, this tree is what we end up with. And you'll notice that hasn't solved the problem. 8 is now part of 10, and 5 and 7 are part of one node. And so that's what we've done here now, is we've said, this was our original situation. And instead of moving 7 up and 5 down, we've moved 5 down and 7 across and 8 up. So we've pulled 2 values from your 3 node. You've pulled one across to take the place of whatever was here, and the other one has moved up. So the value of the parent moved down, that's 5. And now 7 has also moved across, and 8 has moved up. And that can be problematic. It is problematic because now there's the middle node that's underflowing. We've simply moved the problem to the other side. That doesn't help at all. Now if we had a 4 node, we'd be okay. And that is why we check if this is black. If this was red as well, we'd have a 4 node. If we, for example, had 9 sitting here, we could have gone ahead and done that rotation. If there had been a 9 sitting here, we would have been leaving behind a 9, and everything would be fine. We say, okay, we'll go ahead, pull 5 down, pull 7 across, 8 moves up. Our immediate sibling loses 2 values. We take one of those values, the other value moves up into the sibling, but you still had 1 left over. So that is why if the right child had been red, we don't care what the left child was here. We could just go ahead and do this rotation. And 9 would have stayed behind, and 8 would have moved up. And we would be okay. But if this is black, if the right child of 8 here is black, which it is, then that means, okay, this points to a new node. 8 is the greatest value in here, in this node. When we had, again, I need to go back to the original situation. If the right child of 8 is black, then that's saying, in this node containing 7 and 8, 8 is the greatest value. And 8, whatever sits here, is going to be what moves up into the parent. If 8 moves up into the parent, there's nothing left for this node, because it implies 7's got to go across. But if I have 9 as a child of 8 as well, then I say, okay, 8 moves up into the parent, but 9 is still here to hang around. And that would be okay. Because then 8 would move up into the parent, 7 would move over into the other node, 9 would stay here. So that's your difference between case 2A and 2B. Case 2B will say your right child of 8, or the furthest child of 8 from X, is red, so when I do this single rotation, everything is cool. But if in this case, the right child of 8, the furthest child away from X, is black, that means that when I do my rotation, there won't be anything left in my sibling here. I will have moved 5 down into my underflowing sibling. I will have moved 7 across. I will have moved 8 up, and my immediate sibling will now have been rendered empty. And so all we're going to be doing as far as fixing this is saying, well, if I need to fix this, I need to do a rotation. I want to make sure that I've got a red node here, so I'll do a rotation here first. So what you can see is that we're, again, sort of the same thing we had with an insert, where sometimes you were doing a single rotation, sometimes you were doing a double. We're doing basically the same thing here. Case 2B will be the single rotation on 5 that we just wanted to do but couldn't. Case 2A will be, well, let's set that up correctly by doing a rotation on 8. And then once that's done, then we'll be able to do the single rotation on 5. So case 2 overall is sort of like how case 1 had been for insert, where we're saying, okay, ultimately we're doing a double rotation in that situation. If our red node was already here, we do a single rotation. If the red node was here instead, then we do a double rotation on 5. The first part will move the red node, and the second part will then do the original rotation we wanted. So ultimately, all of case 2 is saying, figure out if your red node is far from X, then you just do the single rotation. If it's closer to X, you're going to want to do the double rotation. And either one will then fix things. But we're dividing it up into 2 cases. Case 2B will be the final single rotation. Case 2A will be, if you need to, do this preparatory step first. And that's what we're talking about here. And that's how we always describe double rotations. Double rotation in a direction is the single rotation you wanted to do preceded by a preparatory step of doing a rotation on its child. 2A will be the rotation on its child, that then it must be followed by a rotation on X's parent. I'm sorry. 2A will be the rotation on X's sibling, followed by 2B, which is the rotation on X's parent. And if we hit case 2B without running into case 2A, then we just do the rotation on the parent. So, and of course we got to recolor as well. So we say, okay, if this 2A is our case, then what we are going to do in that situation is we will, we have to look at how this needs to be fixed. We're going to need to color 7 black and color 8 red. So we'll say I should say color sibling red. That's that first step. Do a rotation, a single rotation on sibling away from X. So if X is to your left, as it is in our example, you do a rotation to the right. You're pushing things away from X. If X had been on the other side, if this had been X, you'd be doing a rotation to the left, away from X. So do a rotation away from X, and now the new root of that subtree, which is the, I should say, the new sibling of X is colored black. So you make the sibling red, and then its child will eventually become black. The child moves up to become the sibling. And that's what we see here. We'll take this tree and we'll say we'll say 7. We end up here with this. Let me kind of redraw this here. 10. 5 stays the same. None of this even changes at all. And we say now, okay, 5 points down to a black node 7. 7 points to a red node 8. And then we've got all that. So that's what happens there. This is our 2A is going to move the tree like this, if necessary. If this had been what we saw originally, where the furthest, remember, because this is still X, if the furthest child from X, the furthest child of the sibling from X, had been red, we would have just leapt right to case 2B. Now instead, since the nearer child was red and the furthest one was black, we did the 2A rotation to set up this, and then now we can do case 2B. So you'll either jump right to 2B, or you'll do 2A and then 2B. And that's what we say here. The last thing we do is now go to 2B. And 2B is just going to finish off the rotation operation. All we're going to do now is say, now I finish this off by saying, rotate this way. And so all we've done here is we've retilted the 3 node. We say, let me kind of put the picture back how it was. This was our, when we deleted 2, this was the original picture we had, 7 and 8. But we're saying, the way the 7 and 8 is tilted in our red-black tree is going to cause problems if we do the rotation. So we're going from a node with left child tilting to a node with black node with right red child tilting. We're retilting the 7-8 node to tilt like that, to the right instead of to the left. Now, if I do the rotation here on 5, that will move 5 down, and it will move 7 up. And that's what we want. We want to move 5 down into becoming a child, and 7 will move up to become part of the same node as 10. And so that's our rule here. What we do is we say that the color of the sibling should be made equal to the color of the parent. So this will be whatever color, I should say, whatever, we'll write this out in a moment, whatever color its parent was, in this case it'll be made red, the parent will be made black, and the child here will be made black. And that's what we do. So, what we'll say now is case 2B, if the child of sibling furthest from X is red, then we don't care about the nearer child. That could be red too or black, and that's what we're saying here. We're saying if this had been red to begin with, we don't really care what this is. If it was red or black, everything would still be okay. But if this is black, we're leaving no nodes once we do the rotation. Now that it's red, we will be leaving enough nodes when we do the rotation. Let's go ahead and do this rotation. And that's what we get here. We say 7 moves up, 7 becomes red, because that's what 5 was. So that moves up to become whatever, now sort of part of the node containing 10. And then 5 becomes black. And then this has a null pointer. And 8 will likewise, we know 8 is red, that will likewise become black. And so we've got null here, null here, null here, null here. And you can see that that's now everything is fixed. When we rotate now, 7 is part of the parent. This is a 3 node. Remember, if it's a red child, it's part of the parent above it. So 7 and 10 are together. And then 5 and 8 are 2 of the children of 7, and we can see that here. And then 15 is the other child of 10. And so we have 5, 8, and 12, 15, 16, 5, 8, and then this is all one node, 12, 15, 16. So this solves the problem, and those therefore were our 3 rules. If the child of sibling furthest from X is red, then what we're saying is that red child turns black. Sibling of X, which is the parent of the child you just turned black, becomes whatever color its parent and X's parent is. And then finally, its and X's parent becomes black. And finally, rotate, again, a single rotation. A single rotation on X's parent toward X. And when we write this all out, it just seems a lot more complicated than it really is. All we've done here is we've said, we just changed the colors here. This became black, this became whatever its parent was, this became black, and then we do a rotation here, and we adjust it to this picture. And the wording has to be complicated to cover the more general case of the mirror image as well. But that's the situation here. So that's 2b. And we can say then, after case 2 runs, you can stop. Case 3 is your combined case. So when we deal with the combined case here, that's what we'd be trying to solve here. And so, for example, now take this picture. Let me delete the blue. I'll write that 10 back in there. I'm just sort of cleaning up the diagram here. We're almost done. We've got here. Now, if I were to delete 5, so I say 5 is less than 50, less than 20, less than 10, less than 7. Here's 5. It's a black node. I get rid of it. 7 points to null now, and that's our X. And that's the same as if I'd gotten rid of this. Well, in that case, I need to do a combine, because my sibling here has 2 black children. So 8 doesn't have anything as part of it that I could have done rotations to do a steal like I did in the last case. And so that's what we say here. The assumption here is X is black. The sibling is black. Siblings' children are both black. And remember, null pointers are considered black. So now you have to do a combine. And all you're going to do here to handle the combined case is we'll simply say change sibling to red, and then X points to parent of X. So this is actually the easiest case to handle, even though it's trying to model the most complex operation. What we say here is, I say, well, in this case, all I do is I make the sibling red, And now x is not going to point to where x points to anymore. X will point up to its parent. And that's it. That's all we do for this case 3. However, you say, wait a minute, you got 2 red nodes in a row. You've made 8 red, and so you've got 2 red nodes, and you're right. We need to fix this. And so this now is a continue case. Try to match cases 1 through 3 again with the new x. This is your continue case, so now you say, okay, I've got a new x. Try again to match all the cases 1 through 3. So this is so simple to do, but it also means we need to continue, and that's what we see here. We say I've got a new x now, or actually, let me change that a bit. This really should be rephrased differently so that the next thing doesn't become confusing. Scratch that out in your notes. Let me say this is the continue case. Go back to while loop condition, and then if it is true, then you'd run the loop again. So your while loop's going to take you through these cases over and over. Case 1 is just going to send you to 2A, 2B, or 3. If you hit 2A or 2B, you're done. And then case 3 is going to say, okay, well now you repeat the whole while loop. But you may have made your while loop condition false now. Remember what our while loop condition was. We said, as long as you weren't the root, and as long as x wasn't the root and it was black, you continued. And so, no matter what you do here with 1, 2, or 3, if 3 says, okay, now I'll continue. Oh, wait. If x is either the root now or x is red, you stop. And that's what happens here. We continue on upwards, but now x is red. Now we simply make that black. So what we really have with this subtree now, to kind of draw that again, we say, okay, this hasn't changed. We still have 15, 12, and 16. And we say, okay, 7 is black, 8 was turned red, and that's what we have here. But note, that's what we would have done with a combine. We would have dropped 7 down. We would have combined these 2 nodes into 1. So the parent loses the child, and it loses the value too because 7 drops down. So if 7 drops down and 8 combines with the underflowing node, now you have 7, 8, 12, 15, 16, and 10. So we had a case 3, which just meant color 8 red and move up. And then on this top level, we had a no underflow case, which means you would just leave the while loop. This gets colored black and you're done. If 7 had been the only value in there, and so this node underflowed as well, then you would have gone through the loop again. But we had a no underflow case on its parent, and so we were able to do the same thing we did when we had a no underflow case in the leaf, namely just color some red node black and we'd be done. So that's it. That's case 3, and that's the algorithm. Now this is going to be much like AVL trees. To understand it completely requires going through more examples. But this is the algorithm. You can take this and look over these things as you do more examples. So that's it. Bye for now.